stable and affected from waves floating transit upwards. That is what got many naval engineers sort of excited. And they used to call me some names. But things are developing. So I'll give you, right from the introduction, a first picture of what UNFLOP means. This is a small section of the experimental model, handmade. So UNFLOP is a truss structure with each member of the truss is a floating piece of material of some sort. This particular small structure, which is only about 4.5 meters long, full size, it's 5 by 5 pyramids, has already, this small section has a large number of independent floaters, 62 buoyant truss members. Let's start thinking about that. For millennia, we decided, Earthlings, to start traveling on the water and make ships. And we started building very heavy structures with large bodies, and then these structures had to be had to have a lot of inertia and be heavy in order to push away a lot of weight and mass of water and be able to withstand the waves, to have stability. That was the concept. But we have seen that this kind of concept with large watertight compartments and large bodies doesn't really pay off. We've had many examples of that. This kind of structure, for example, has 4 huge legs. If one leg breaks, or 2 legs break, there are problems. It's not necessary that the overall buoyancy of any floating structure must be created by 1 or 2 or 4 large volume bodies. That doesn't have to be, it's not a necessity. Archimedes never said that. But we decided to do that for a long time. Smaller bodies are affected much less by wave motion. And so they don't have, if the structure is created by a large number of small floating bodies, then it doesn't have to be heavy, because it doesn't have to have so much inertia to fight the waves, because the effect of the waves is small on each body, and the wave acts on each body. So the smaller the body, the less the effect. We all know what happened when Deepwater Horizon lost 2 legs and the Alexander Keelan lost 1. Big disasters. So let's look at the concept. This is actual design of the scale model, which is a pyramid structure truss with cylindrical shaped truss elements. It's meant to be in a fixed location on the water, and we can do anything we like with it. And we have modularity, standardization, scalability, design flexibility, anytime expandability. Now some tourist industry guy or lady will get some funny ideas, like we can build something like that near shore or in a difficult condition. The same structure can be a tourist installation, have its own heliport, have its own protected marina area, and we make a lot of money. One possibility. Now, this structure can expand. We can build the pyramids or whatever truss is upwards, or extend it horizontally. And we can even build and extend a structure that has been there already working for some time. It's very easy. It's individual members. Now, it comprises of pyramid shape or triangle or orthogonal basic truss elements that are formed by individually buoyant, watertight, maybe, if we want to have an empty thing that we can use for ballast water, or solid truss members. Solid, I mean composite materials of high durability that will actually give the total structure its buoyancy. And they are connected with articulated or fixed joining systems. We'll see in a minute. And that's why it's so easy to assemble it, disassemble it, do anything you like, even inside the water. Stable, unaffected from waves, because you can't break all this large number of individual buoyant members, too many of them, just like that. And most of them would be solid bodies that cannot lose the buoyancy. They're like cork. You can't sink cork. And for the waves, the fluid molecules, the water molecules moving up and down, are hitting in millions of forces, in millions of directions, the surfaces that they see in front of them. But all these are microforces that basically cannot concentrate altogether into one big force to act on the total structure. The inertia of the structure cannot be influenced by these individual forces. There's many ways that we can moor it. Depending on the application, there's good state-of-the-art from naval engineering. And when it comes to specific applications, we find ways to do it. And of course, there was the first test in that swimming pool. That was a lot of fun. You can find it on the YouTube. All the friends were crazy, screaming and jumping in and out of the water. We can have other forms of structure we can add to the pyramid structure, also vertical members, and have a combination of pyramids and orthogonal shapes, and increase flotation and load capability depending on the application. Or it can be just orthogonal and sort of for easy, low-cost applications. Now, the top surface can also, this is supposed to float to about 50 or 60% of the height of the structure. But you can actually have also floating members on the top surface that will form a last kind of flotation touching on the still water level. And still the structure won't be affected by waves. This is one design that we're using now for the joints. It works very nice. You can make both fixed or articulated joint. And what was very interesting from the first simulations was that the structure has inherent capability of absorbing wave energy. That means it's a floating breakwater. And maybe we can figure out if that can also play a big role related to tsunamis. I don't know yet. Maybe this is a big claim, but we will see. So, the first simulations. This is the small scale model, which is 4.5 meters on the side. 5 by 5 pyramids. And we see, first of all, this is completely free in the water, so the effect of wave can be seen also on the horizontal axis. Now you see that we have already an effect of absorption of the wave energy. And we can see it even more when we look at it from top. Now these simulations were done in Xianjiang Liverpool Campus University in Suzhou, China. by a group here led by Dr. Spiros Kavnis that we discovered each other suddenly last year. And they got very interested, and the university helped a lot to do this initial research. This model is, the physical size of this model is 100 by 100 meters. Each truss member is 10 meters long. And it's the first demo that I hope we can build soon. And we again see the wear absorption effect. Now this is a 35-meter wavelength. In the next one, we'll see the same structure with 50-meter wavelength. So we actually have 2 waves or 3 waves in the width of the structure, and the effect is again the same. We don't have any vertical movement, and we have very clear wave energy absorption. And the extreme case I wanted to see with my own eyes is that when the wavelength is longer than the width of the structure, of course then would have some influence, there's no question about that. So we have to take that into account when we build things. Now these are the graphs, and there's very details about this first initial research, and it's very good. So this is what they provided at the Xianjiang, a big cluster to do this research, this CFD, because it was very demanding. Now, the truss can also have members with hydrodynamic shapes, because we can use it in moving water as a support structure for example, marine renewable energy converters in tidal or current situations. And then we have torpedo shape and hydrofoil shape members to reduce drag. But also this structure can actually be propelled in the water very efficiently because of its shape. So that's what we call UNFLOP ship. And with this structure we can sort of, this is just a quick image I had prepared to show the concept. It's not an engineering design, we're not going to make the thing looking like that. The principle is that the hull will be above the height of the waves. The structure will be very stable because we also have on the surface of the water torpedo-shaped members, and it can be properly engineered. It's good naval engineering around. So we can use energy mostly to transport the payload, not the actual structure, because until now we have very big ships, and we waste a lot of energy to move the empty ships instead of the payload. Applications. I don't know which application to stress more. We talked about waterborne transfer. Of course, we need to talk about ocean renewable energy and various other things. You can do anything with a safe, floating, earthquake-proof real estate. So let's look at the marine renewable energy sources integrated application platform. We have this structure, we have it as an enabling base on which we can mount any kind of energy converters from wind or water or whatever. This is also the other technology, and this is an image from the wind tunnel in the National Technical University of Athens, where we tested for a long time 3 handmade prototypes that showed the way for the development. And the idea is, we can call it a vertical axis turbine. This is the design program of the prototype, which was great to look at it. So we have airfoils that are free to move by a small angle, and in both positions they can absorb energy using both fluid dynamics forces, drag and lift, all the time. In other words, the angle of attack of the fluid on the surface, either inside or outside, always changes all the time between drag and lift mode, and the only thing that wastes energy from the fluid molecules, kinetic energy, is the turbulence we might get the vortices at the edges, and that's what we're investigating right now. This is another design, and I'm explaining here in simple ways the philosophy of this operation, but we can go straight away to the simulation, the preliminary simulations that are being done in Spain, another group that got very interested in these technologies. And these preliminary simulations actually want to make a base. We don't have the airfoils there or hydrofoils changing position. They have fixed position, and we're doing some measurements to see what happens with the vortices and the turbulences, and then it would be a base to see further, and then we're comparing that to the existing bibliography to see what happens in real life when the blades actually are able to move. The blades change position depending on the flow they see coming to them. And they always take one or the other position in order to have also absorption all the time from both fluid dynamics forces. So that's the simulation, and the big machinery computational power at UBC in Spain that is necessary for this kind of simulations. I'll put it in a simple way. I think this turbine technology is mimicking real life, how birds fly and fish swim. There's a good relationship between the machine, if you like birds or fish, and the moving molecules. They keep changing their wings and their fins in order to have a good relationship with the fluid molecules that move. The same thing is done with this new technology I'm presenting. And we probably all know what are the shortcomings of the existing technologies. Shortcomings, we know Bert's limit, we know the actuator disc philosophy, and these machines, the two on the right, use only lift forces. Savonius uses only drag forces. A lot of kinetic energy is lost.
Excuse me. You do concrete.
Right. So we can put all kinds of converters on this platform of any size, and we can draw energy from all renewable sources that are available in the ocean. And this is the concept of the wave converter from this technology, because each hydrofoil produces energy, and it doesn't matter if the water goes up and down. So these are the existing technologies for wind turbines floating, and the problem is that whatever is being developed at the moment, it's not looking at concentrating different converters on one spot so that we can take all the electricity and take it out with one cable. And even with marine energy, the same thing is happening. And there was some attempt by the European Union with the Marina platform, and there were some ideas to have some wind turbines and wave converters together. And there was recently the Ocean of Tomorrow project that is trying to do the same thing with various ideas. These are the things that the Mermaid project from the Ocean of Tomorrow, and the Tropos project of the ocean of tomorrow. But still, we don't know how to build this and how they're going to float in the ocean. And with this platform, we can take the existing wind turbines, the spar-buoy type, and make it much cheaper, make it fixed, the nacelle doesn't have to turn, and if they are fixed on the platform, the whole platform can actually seek the wind. It's a matter of a bit more engineering study to see how this is possible. So wind turbines that exist with existing any kind of technology of wave converters and maybe tidal if it's on coil size can play together on one spot. This is a quick idea for an application that is needed for establishing wind and wave resource in the ocean in order to decide where we're going to build our farms.
Excuse me.
And we can also put AWTEC on this, and I'm concluding, Mr. Chairman. With what we all know about ocean thermal energy conversion, and the most important thing is that the last plate that I'll give it to you, just to think about it.
Okay, thank you.
I'm sorry if I took a little longer, it's a lot of material.
Just 1 minute for question. Is there any question or comment? Okay, please.
Have you ever considered the mooring force for such structure?
Ever consider what?
Mooring. The challenge in mooring.
Yes.
Mooring, yeah.
Yes.
Because from your simulation, I can see the structure may create a lot of drag due to the massive of truss system, right? So potentially it will create huge mooring force.
We've done the naval engineering analysis. I have the naval engineering department of the National Technical University of Athens thinking about it. And yes, there is technology that we can do the mooring depending on the application in the best possible way.
Thank you. Second question, how about the reserve buoyancy? Because I see your structure, it is rigid, it can flow by itself, but how much reserve buoyancy you design based on this concept to support your payload?
Yeah. Well, you can build as much as a reserve buoyancy you like. It's an engineering issue. When you start doing an application, you can even increase the buoyancy afterwards. When you build something, you can put more buoyancy on it after you build it.
Last comment is perhaps you should do an economic analysis, look at the cost and benefit. Thank you.
Thank you.
Okay, thank you very much.